Okay, so today we're going to be talking about acid-base equilibrium. So we're going to start with some important notes. So important notes, just overall for this unit are the stronger the acid, the weaker its conjugate base, which would make sense because if you have a strong acid and it has a really large Ka and it dissociates a ton, then obviously the conjugate base is going to be weaker. Um, and then just another important note that can sometimes be confusing to people is that weak bases are often without OH minus, and they instead react with water to produce OH minus. So, for example, NH3, that will react with water to produce OH minus and ammonium and the ammonium ion. So that's just something that people can get confused about. Okay, so then we have some terms to know also. Um, so monoprotic acids are acids that are donating one H plus, so HCl would be an example. Diprotic, diprotic acids are donating two or more H pluses, so like carbonic acid. Polyprotic acids are acids donating three or more H pluses, so that would be phosphoric acid. And then another term that can be confusing or you can just forget about is amphiprotic and amphoteric. Those mean the same thing. And it means that it's molecules or ions that can behave as either acids or bases. So an example of that would be water, because water can accept a proton, but it can also donate one. So it can accept one to form the hydronium ion, or it can donate one and become OH minus. And then just another thing that I've seen on tests before, a question about standardization, which just means performing a titration to find the exact molarity of a substance. So next, we're going to talk about finding Ka and Kb. So um, for weak acids, we're going to look at this equation here, and we're going to do products over reactants as usual, and so it's pretty self-explanatory. We're obviously not including the H2O because that's a liquid, and we're doing concentrations with aqueous solutions, so we're not using the liquid. And then it's just very similar for Kb, but basically the reaction goes a different direction, and there's OH minus instead of H3O plus. So that's how to find Ka and Kb. Pretty self-explanatory and similar to finding Kp and Kc. Um, okay, so next we're going to talk about Kw, which is the ionic product constant of water. And it's especially helpful in its application because Ka times Kb equals Kw, so you can solve for Ka or Kb um, using that expression if you know one of them. So that's like the best application of it. And then this diagram right here or this expression right here just sort of shows like what it is. Um, so it's most helpful in its application. So next we're going to talk about buffers. So buffers are made up of high amounts of a weak acid and its conjugate base. They're highly resistant to changes in pH brought on by the addition of a strong acid or a strong base. And the pH is almost equal to the pKa. And so therefore the H plus is approximately equal to the Ka. So um, there's this equation which is really important. So right here, this is the Henderson-Hasselbalch equation. I actually prefer these two equations on the side, the ones that are equal to the concentration of H plus. I just think they're a little bit easier to understand and easier to plug into, but the Henderson-Hasselbalch equation you can also use if you like that equation better. So I'm just going to go into a little bit of explanation about these equations. So the ratio of the concentrations of the weak acid and its conjugate base is equal to the mole ratio because they're in the same solution. So the volume's constant. So that should make sense. So that's why in the second equation here, you can use the mole ratio. They just switch the mole ratio for the concentration ratio. And that's fine because they're in the same solution, so it's the same volume. And then just another important note, diluting a buffer with water does not change the pH because the total volume is not used in either of these equations. So notice how volume is not involved in any of these. So you can dilute a solution as much as you want and it will not change the pH. Okay. So now we're going to talk about buffer capacity and buffer range. So buffer capacity is basically how much OH minus or H plus a buffer can absorb before becoming ineffective. Pretty self-explanatory. It can only absorb so much before it's going to start, the pH is going to start changing rapidly. And then the buffer range would be the pH over which the buffer is effective. So that's, again, pretty self-explanatory from those words. So acid-base indicators, they can help determine the equivalence point. So that's where the moles of acid equals the moles of the base in an acid-base titration. And if an indicator is chosen properly, it will reach its endpoint, which is when it changes colors, not to be confused with equivalence point, at the equivalence point of the titration. So it's best to choose an indicator based on the pH of the equivalence point so that it will reach its endpoint at the equivalence and be of use to you. So just some other things about acid-base titration. So a titrant is the substance in the burette. That's something that's come up on test questions before, and it can be like hard to remember what that is, if that's the substance in the burette or the substance in the beaker or whatever, or the Erlenmeyer. So that's just an important term. And then another important thing is particularly looking at a titration with a weak acid or a weak base and a strong acid, strong base. So that would be, so at half equivalence, the pH equals the pKa, and so obviously the Ka equals the H+. So that's just an important connection to make because that comes up in a lot of problems. Okay, so now we're going to talk about salt solutions. So salts can actually be neutral, basic, or acidic. So a neutral salt would be when the cation forms a strong base with OH minus and the anion forms a strong acid with H plus. So an example of this would be NaNO3 because Na forms the strong base NaOH and NO3 forms the strong acid HNO3. So we know that neither of those are going to actually bond when in solution because they're both strong. So that's a neutral salt. And there's going to be about equal amounts of OH minus and H plus. So then a basic salt would be when the cation forms a strong base with the OH minus. So in this example we have potassium acetate, so that would be KOH, and the anion forms a weak acid with the H plus. So the that would be acetic acid, so HC2H3O2, and that would pull an H plus out of the solution because it bonds with the anion. So it's bonding with the acetic or the acetate ion, and it makes the solution more basic because it's pulling out the H plus and leaving OH minus there. And the KOH, since that's a strong base, it's not going to bond because it's in solution. So the solution is going to be left with a lot more OH minus than H plus. And then finally, so an acidic salt is pretty much the opposite of a basic salt. So that would be when the cation acts as a weak base in solution and the anions form a strong acid with the H plus. So an example of this would be NH4Cl. So NH4 in this example will donate an H plus, which will be accepted by the water, forming a hydronium ion, which would make the solution more acidic. And then finally, we're going to talk about percent ionization. So this is just important because it comes up in a lot of the textbook problems. So percent ionization, it makes a lot of sense if you think about it. It's the concentration of the H plus at equilibrium over the concentration of the acid at, that's like the the initial concentration of the acid, and then times 100 to get the percent. So that's makes a lot of sense, pretty straightforward. So thank you for watching.